Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 9th and 10th centuries witnessed a remarkable flourishing of intellectual activity across the Islamic world, a period often referred to as the Islamic Golden Age. Centers of learning thrived in cities like Baghdad, Cairo, and Cordoba, attracting scholars from diverse backgrounds and fostering an environment of intense scientific inquiry. Within this vibrant landscape emerged a figure whose contributions to astronomy and mathematics would resonate for centuries. Muhammad ibn Jabir ibn Sinan al-Battani, often Latinized as al-Battani, was born around 158 CE in or near Harran, a city in Upper Mesopotamia, now part of modern-day Turkey. Harran held a unique place in the intellectual history of the region. Long after the rise of Islam, it remained a center of paganism, particularly for the Sabian sect. While the precise nature of al-Battani's family's connection to the Sabians remains a matter of scholarly debate, the cultural and intellectual milieu of Harran undeniably influenced his early development. The Sabians, known for their syncretic beliefs that blended elements of ancient Mesopotamian religion with Greek philosophy and Hermeticism, maintained a strong tradition of astronomical and mathematical study. They saw the celestial bodies as divine entities and believed that understanding their movements was key to unlocking cosmic secrets. This emphasis on astronomy and mathematics likely played a crucial role in shaping al-Battani's intellectual trajectory, providing him with a foundation upon which to build his later achievements. The world into which al-Battani was born inherited a complex legacy of astronomical knowledge. The dominant model for understanding the cosmos was that of Claudius Ptolemy, the 2nd century Greco-Egyptian astronomer, whose *** had become the standard reference work for astronomers across the Mediterranean world and beyond. Ptolemy's geocentric model, which placed the Earth at the center of the universe with the sun, moon, planets, and stars revolving around it, had provided a comprehensive framework for understanding celestial phenomena. The ** also contained a wealth of astronomical data, including star catalogs and tables of planetary motion. However, by the 9th century, limitations within the Ptolemaic system had become increasingly apparent. Astronomers found that the model did not always accurately predict the positions of celestial objects, and there were discrepancies between Ptolemy's theoretical framework and empirical observations. One significant challenge lay in the accuracy of the astronomical parameters used in Ptolemy's models, such as the length of the solar year, the obliquity of the ecliptic, the angle between the Earth's equator and its orbital plane, and the eccentricity of the planetary orbits. Small errors in these parameters could lead to significant inaccuracies in astronomical calculations, making it difficult to predict eclipses, planetary conjunctions, and other celestial events. Furthermore, the instruments available to astronomers at the time were relatively crude, limiting the precision with which they could make observations. Sundials, astrolabes, and quadrants were the primary tools used to measure the positions of stars and planets, but these instruments were subject to various sources of error, including atmospheric refraction, parallax, and imperfections in their construction. Overcoming these limitations required not only improved observational techniques, but also a deeper understanding of the underlying mathematical principles governing celestial motion. Al-Battani recognized these shortcomings and dedicated himself to refining astronomical knowledge through meticulous observation and rigorous mathematical analysis. He understood that improving the accuracy of astronomical predictions required a multi-pronged approach, one that combined precise measurements with sophisticated mathematical tools. Al-Battani's early work focused on mastering the existing body of astronomical knowledge, including Ptolemy's *** and the astronomical tables produced by earlier Islamic astronomers. He immersed himself in the study of mathematics, recognizing its crucial role in understanding and predicting celestial phenomena. In particular, he focused on trigonometry, the branch of mathematics that deals with the relationships between the sides and angles of triangles. Trigonometry provided the essential tools for calculating the positions of celestial objects on the celestial sphere, for converting between different coordinate systems, and for solving a wide range of astronomical problems. While Greek astronomers had developed the foundations of trigonometry, al-Battani made significant advancements in this field, particularly in the development of trigonometric functions. He fully embraced the sine function, which had been known in India, but had not been widely used by Greek astronomers. Al-Battani recognized the power of the sine function for simplifying astronomical calculations and incorporated it into his own work. He also developed the cosine function, which is closely related to the sine function, and began exploring the tangent function, which relates the sine and cosine. Al-Battani's use of sines, cosines, and tangents was a significant departure from the geometric methods used by earlier astronomers. By expressing trigonometric relationships in terms of these functions, he was able to simplify complex calculations and develop more efficient methods for solving astronomical problems. He also recognized the importance of these functions for creating accurate astronomical tables, which could be used to predict the positions of celestial objects at any given time. His work in trigonometry laid the groundwork for his later astronomical achievements. By mastering these mathematical tools, he was able to analyze his observational data with greater precision and develop more accurate models of celestial motion. His commitment to both observation and mathematical rigor set him apart from many of his contemporaries and established him as one of the leading astronomers of his time. Al-Battani's journey began with a deep dive into the existing astronomical knowledge and a recognition of its limitations. He sought to build upon this foundation through his own observations and mathematical innovations, ultimately aiming for a more accurate and comprehensive understanding of the cosmos. His early life, immersed in the intellectual traditions of Harran, combined with his dedication to rigorous study, shaped him into a pivotal figure in the history of astronomy. Al-Battani's mastery of mathematics provided the essential foundation for his astronomical pursuits. Armed with these tools, he embarked on a series of groundbreaking observations that would reshape the understanding of the cosmos. He recognized that existing astronomical data, inherited from the Greeks and refined by generations of scholars, contained inaccuracies that needed correction. He aimed to provide more accurate and reliable information about the movement of celestial bodies. One of al-Battani's most significant achievements was his precise measurement of the solar year. Previous estimates, including those of Ptolemy, suffered from accumulated errors that led to discrepancies between predicted and actual astronomical events. Al-Battani, through meticulous observation and calculation, determined the length of the solar year to be 365 days, 5 hours, 46 minutes, and 24 seconds. This value is remarkably close to the modern accepted value, demonstrating the accuracy of his methods and instruments. This improved measurement had a direct impact on the accuracy of calendars and astronomical predictions, ensuring that they remained synchronized with the actual movements of the sun. Another crucial parameter in astronomical models is the obliquity of the ecliptic, the angle between the Earth's equator and the plane of its orbit around the sun. Accurate determination of this angle is essential for calculating the seasons and predicting the positions of the sun and other celestial objects throughout the year. Al-Battani undertook careful measurements of the obliquity, obtaining a value of 23 degrees and 35 minutes. While this value differs slightly from modern measurements, it represented a significant improvement over previous estimates and contributed to more accurate astronomical calculations. Solar and lunar eclipses provided valuable opportunities for astronomers to test their theories and refine their models. Al-Battani devoted considerable attention to observing and analyzing these celestial events. He meticulously recorded the times and magnitudes of eclipses, using this data to refine his understanding of the moon's orbit and its relationship to the sun and Earth. His observations of eclipses allowed him to improve the accuracy of eclipse predictions, a matter of considerable importance for both scientific and practical purposes. The ability to predict eclipses accurately was viewed as a sign of astronomical prowess and had implications for calendar keeping and religious observances. Perhaps one of al-Battani's most profound discoveries was his observation that the apparent position of the sun's apogee, the point in its orbit farthest from the Earth, was gradually changing over time. This phenomenon, known as the precession of the equinoxes, had been noted by earlier astronomers, including Hipparchus, but al-Battani was able to determine its rate with greater precision. His calculations suggested that the sun's apogee was moving at a rate of approximately 55 seconds of arc per year. The discovery of the precession of the equinoxes had far-reaching implications for astronomical theory. It challenged the established Ptolemaic model, which assumed that the celestial sphere was fixed and unchanging. Al-Battani's observations provided evidence that the cosmos was more dynamic and complex than previously thought. This discovery paved the way for future astronomers to develop more sophisticated models of the universe that could account for the observed changes in the positions of celestial objects. It demonstrated that the seemingly immutable heavens were in fact subject to gradual but significant shifts. Astronomical instruments of al-Battani's era presented inherent limitations. The accuracy of observations was constrained by the precision of the instruments themselves and the techniques used to operate them. Al-Battani recognized these limitations and sought to overcome them through innovation and ingenuity. He designed and constructed his own astronomical instruments, including quadrants, astrolabes, and sundials, paying careful attention to their accuracy and ease of use. He also developed improved observational techniques, such as using multiple observations to reduce errors and employing sophisticated mathematical methods to analyze his data. Al-Battani's tables found practical applications beyond the realm of pure astronomical research. They became essential tools for determining the time of day, a crucial factor for regulating daily life and scheduling religious observances. In Islamic practice, the timing of prayers is determined by the position of the sun. Al-Battani's tables provided the necessary information to calculate these prayer times accurately, ensuring that Muslims could fulfill their religious obligations at the correct times. His work, therefore, had a direct impact on the daily lives of people throughout the Islamic world. Through a combination of meticulous observation, innovative instrumentation, and sophisticated mathematical analysis, al-Battani made significant advances in the field of astronomy. His measurements of the solar year, the obliquity of the ecliptic, and the precession of the equinoxes refined existing astronomical models and provided a more accurate picture of the cosmos. His work challenged established theories and paved the way for future discoveries. His commitment to precision and accuracy, combined with his deep understanding of mathematics, established him as one of the most influential astronomers of his time. His legacy extends far beyond his own era, shaping the course of astronomical research for centuries to come. He exemplified the power of combining theoretical knowledge with empirical observation, a hallmark of scientific inquiry. Al-Battani's contributions extended far beyond mere observation. He revolutionized the mathematical tools used to understand the cosmos. His profound impact on trigonometry, particularly the systematic development and application of trigonometric ratios, fundamentally reshaped astronomical calculations and paved the way for later scientific advancements. He moved beyond the limitations of earlier geometric approaches, ushering in an era of greater precision and analytical power. Before al-Battani, astronomers primarily relied on the chord function, a geometric concept used extensively by Ptolemy in his asterisk Almagest asterisk. The chord function related the length of a chord in a circle to the angle subtended by that chord at the center. While effective, this approach proved cumbersome for complex calculations. Al-Battani recognized the potential of what would become the modern sine function, a concept easier to manipulate algebraically and far more amenable to creating comprehensive tables. He essentially replaced the chord function with the sine, streamlining calculations and opening new avenues for astronomical inquiry. This transition marked a significant conceptual shift, moving away from purely geometric interpretations toward a more abstract and powerful trigonometric framework. Al-Battani also introduced related trigonometric ratios, including the cosine, tangent, and cotangent. He meticulously defined these functions and explored their relationships, establishing a coherent system of trigonometric functions. This systematization was crucial for simplifying astronomical calculations, allowing astronomers to express complex geometric relationships in terms of these standardized ratios. He understood that these functions, when properly tabulated, could dramatically reduce the computational burden associated with astronomical predictions. One of al-Battani's most significant achievements lay in his creation of highly accurate trigonometric tables. Prior tables suffered from inaccuracies, limiting the precision of astronomical calculations. Al-Battani, through careful observation and meticulous computation, constructed tables of sines, cosines, tangents, and cotangents with significantly improved accuracy. These tables, a product of immense labor and mathematical skill, became indispensable tools for astronomers. They allowed for more precise determinations of planetary positions, eclipses, and other celestial phenomena. The increased accuracy of these tables reflected al-Battani's commitment to empirical verification and his deep understanding of the underlying mathematical principles. The construction of these tables was a monumental undertaking, requiring a combination of theoretical knowledge and computational prowess. Al-Battani likely used iterative methods and interpolation techniques to calculate the values of the trigonometric functions for small increments of angles. His dedication to accuracy is evident in the precision of his results, which surpassed those of his predecessors. These tables were a testament to his mathematical skill and his unwavering commitment to improving the accuracy of astronomical calculations. Al-Battani's mastery of trigonometry found practical application in solving a wide range of astronomical problems. He employed trigonometric methods to determine the positions of stars and planets, calculate the angles of elevation and azimuth, and predict the occurrence of eclipses. These calculations, essential for creating accurate astronomical tables and calendars, demanded a deep understanding of both trigonometry and celestial mechanics. Determining the positions of celestial objects posed significant challenges in al-Battani's time. Astronomers had to contend with atmospheric refraction, parallax, and the complexities of planetary motion. Al-Battani developed sophisticated techniques to account for these factors, using trigonometry to correct for observational errors and refine his calculations. He understood that accurate astronomical predictions required not only precise observations, but also a thorough understanding of the mathematical principles governing celestial phenomena. Spherical trigonometry, a branch of trigonometry dealing with triangles on the surface of a sphere, proved particularly useful in solving astronomical problems. Al-Battani made significant contributions to this field, developing formulas for solving spherical triangles. These formulas allowed astronomers to calculate the distances and angles between celestial objects, essential for determining their positions and predicting their movements. He understood that the celestial sphere could be modeled mathematically using spherical trigonometry, providing a powerful tool for understanding the cosmos. One of al-Battani's key contributions to spherical trigonometry was his formula for calculating the angle between two great circles on a sphere. This formula, a cornerstone of spherical trigonometry, found widespread application in astronomy and navigation. It allowed astronomers to determine the angular separation between stars, planets, and other celestial objects, providing crucial information for mapping the sky and predicting celestial events. His innovative approach to trigonometry simplified the complex calculations involved in astronomy. By replacing geometric methods with algebraic techniques, he streamlined the process of determining planetary positions, predicting eclipses, and constructing astronomical tables. His work made astronomy more accessible to mathematicians and scientists, fostering further advancements in the field. He understood that a more efficient and elegant mathematical framework could unlock new insights into the workings of the cosmos. Al-Battani's adoption of the sine function, his systematic development of trigonometric ratios, and his creation of accurate trigonometric tables revolutionized astronomical calculations. His work not only improved the precision of astronomical predictions, but also simplified the mathematical tools used by astronomers. He transformed trigonometry from a collection of geometric techniques into a powerful algebraic system, paving the way for future advancements in astronomy and mathematics. His legacy as a master of trigonometry and a pioneer of astronomical calculation remains secure. Al-Battani's accumulated knowledge and groundbreaking techniques found their most comprehensive expression in his Kitāb az-Zīj or Book of Astronomical Tables. This monumental work stands as a testament to his observational skill, mathematical prowess, and dedication to advancing the science of astronomy. The Kitāb az-Zīj represents the culmination of centuries of astronomical thought, synthesizing Greek, Indian, and Islamic traditions into a cohesive and innovative framework. The problems that al-Battani sought to address with the Kitāb az-Zīj were multifaceted. Foremost among them was the improvement of astronomical predictions. Existing models, often based on Ptolemai's ***, suffered from inaccuracies that became increasingly apparent with continued observation. Al-Battani aimed to refine these models, incorporating his own precise measurements and novel mathematical techniques to achieve greater predictive power. He also sought to simplify astronomical calculations, making them more accessible to astronomers and mathematicians. The complex geometric methods prevalent in earlier works could be cumbersome and time-consuming. Al-Battani's adoption of trigonometric functions and algebraic methods offered a more streamlined and efficient approach. The Kitāb az-Zīj is meticulously organized, reflecting al-Battani's systematic approach to astronomical research. It encompasses a wide range of topics, including a catalog of stars with their positions and magnitudes, tables for calculating the positions of the sun, moon, and planets, discussions of solar and lunar eclipses, methods for determining the time of day, and explanations of various astronomical phenomena. The book is divided into 57 chapters, each dedicated to a specific aspect of astronomy or mathematics. Al-Battani's Kitāb az-Zīj presents his findings in a clear and accessible manner, combining theoretical explanations with practical examples and detailed tables. He meticulously documents his observational data, providing a valuable resource for future astronomers. He also explains the mathematical methods he employed, allowing readers to understand and replicate his calculations. The book is notable for its emphasis on accuracy and precision, reflecting al-Battani's commitment to empirical observation and rigorous mathematical analysis. Specific examples illustrate how al-Battani utilized the Kitāb az-Zīj to solve astronomical problems. Determining the time of day, a crucial task for religious observances and practical purposes, could be accomplished using the tables and methods outlined in the book. By measuring the altitude of the sun or a star and consulting the appropriate tables, one could calculate the local time with considerable accuracy. Similarly, calculating the position of a planet at any given time involved a series of steps outlined in the Kitāb Kitāb az-Zīj ***. These steps included consulting planetary tables, applying trigonometric formulas, and making corrections for various astronomical effects. Al-Battani provided detailed instructions and examples to guide the reader through these calculations. The Kitāb az-Zīj also addressed the prediction of solar and lunar eclipses, phenomena of great interest to both astronomers and the general public. Al-Battani refined the methods for predicting eclipses, incorporating his own observations and mathematical insights. He provided tables and formulas that allowed astronomers to calculate the time, duration, and magnitude of eclipses with improved accuracy. His work on eclipses demonstrated the power of his mathematical techniques and his deep understanding of celestial mechanics. The influence of the Kitāb az-Zīj on later Islamic and European astronomers cannot be overstated. It became a standard reference work, widely consulted and cited for centuries. Its comprehensive coverage of astronomy, its accurate observational data, and its clear explanations of mathematical methods made it an invaluable resource for scholars and practitioners alike. The Kitāb az-Zīj played a crucial role in transmitting al-Battani's knowledge to subsequent generations, ensuring the continuation and advancement of astronomical research. In the Islamic world, the Kitāb az-Zīj was widely disseminated and studied. Astronomers such as Ibn Yunus and al-Biruni drew heavily on al-Battani's work, incorporating his observations and methods into their own research. The Kitāb az-Zīj served as a foundation for further advancements in astronomy, inspiring new investigations and refinements of existing theories. Its impact extended beyond the realm of astronomy, influencing other fields such as mathematics, geography, and timekeeping. The Kitāb az-Zīj also had a profound impact on European astronomy. In the 12th century, the book was translated into Latin, making it accessible to European scholars. The Latin translation, known as *de Scientia Stellarum* on the science of the stars, became a standard textbook in European universities. European astronomers such as Copernicus, Tycho Brahe, and Kepler drew heavily on al-Battani's work, incorporating his observations and methods into their own research. Al-Battani's trigonometric tables, in particular, proved to be invaluable to European astronomers. His accurate values for the sine, cosine, and tangent functions allowed them to perform astronomical calculations with greater precision. His work on spherical trigonometry provided essential tools for solving problems related to celestial navigation and mapmaking. The Kitāb az-Zīj played a crucial role in the transmission of Islamic scientific knowledge to Europe, contributing to the intellectual ferment of the Renaissance. The Kitāb az-Zīj's influence extended beyond the Renaissance, continuing to shape astronomical research in subsequent centuries. Its observational data remained valuable even as new telescopes and instruments were developed. Al-Battani's mathematical methods, particularly his use of trigonometry, continued to be employed in astronomical calculations. The Kitāb az-Zīj stands as a lasting testament to al-Battani's genius and his enduring contribution to the science of astronomy. It represents a synthesis of ancient wisdom and innovative thinking, bridging the gap between Greek astronomy and modern science. Al-Battani's legacy resonates deeply within the annals of astronomy and mathematics, a testament to his profound influence on the trajectory of scientific thought. His work served as a critical conduit, channeling the intellectual currents of the Islamic Golden Age into the burgeoning scientific landscape of Renaissance Europe. The precision of his astronomical observations and the elegance of his trigonometric methods found fertile ground in the minds of later astronomers, shaping their theories and propelling the scientific revolution. Consider the monumental contributions of Nicolaus Copernicus. His heliocentric model, which revolutionized our understanding of the cosmos, owed a significant debt to al-Battani's meticulous observations. Copernicus, in his *De Revolutionibus Orbium Celestium*, frequently cited al-Battani, acknowledging the accuracy and reliability of his data. Al-Battani's determination of the solar apogee, the point in Earth's orbit where it is farthest from the sun, proved particularly valuable to Copernicus. This measurement, refined through centuries of observation, provided crucial empirical evidence for Copernicus's model and allowed him to refine his calculations of planetary orbits. The very tables Copernicus employed benefited from al-Battani's earlier work on trigonometric functions, enhancing the accuracy of planetary position predictions. Tycho Brahe, the Danish astronomer renowned for his unparalleled observational precision, stands as another beneficiary of al-Battani's legacy. Brahe's meticulous measurements of stellar and planetary positions, conducted at his Jörneborg Observatory, formed the bedrock upon which Johannes Kepler formulated his laws of planetary motion. Brahe's commitment to observational accuracy mirrored al-Battani's own dedication. Brahe's work implicitly validated the importance of the detailed, long-term observations that al-Battani had pioneered. The sheer volume and reliability of al-Battani's data provided a historical benchmark against which Brahe could calibrate his own instruments and assess the consistency of his findings. Johannes Kepler, building upon Brahe's observational data, formulated his 3 laws of planetary motion, forever altering our understanding of celestial mechanics. Kepler's laws, which describe the elliptical paths of planets, their varying speeds, and the relationship between their orbital period and distance from the sun, represented a paradigm shift in astronomy. While Kepler's genius lay in his ability to discern mathematical patterns within observational data, the quality and availability of that data were paramount. Al-Battani's earlier work, transmitted through the Kitāb az-Zīj, provided a valuable resource for Kepler, offering a historical context for his own observations and a means of verifying his calculations. Kepler's reliance on accurate trigonometric functions, essential for calculating planetary positions, further underscores the enduring impact of al-Battani's mathematical contributions. The development of trigonometric tables, a cornerstone of al-Battani's mathematical achievements, provided astronomers with essential tools for solving problems related to spherical astronomy and celestial navigation. These tables, which provided accurate values for sine, cosine, tangent, and cotangent functions at various angles, greatly simplified astronomical calculations, and improved the precision of planetary position predictions. The impact of these tables extended far beyond astronomy, influencing fields such as surveying, cartography, and navigation. Mariners relied on trigonometric tables to determine their position at sea, while surveyors used them to measure distances and angles on land. The widespread adoption of trigonometric tables, facilitated by the translation of Islamic scientific texts into Latin, contributed to the practical applications of mathematics and the advancement of scientific knowledge. The scientific revolution, a period of profound intellectual and scientific transformation in Europe, witnessed a shift from Aristotelian philosophy and Ptolemaic astronomy to a new emphasis on empirical observation, mathematical reasoning, and experimental verification. Al-Battani's work, with its emphasis on precise observation and mathematical rigor, played a crucial role in this transition. His astronomical observations challenged the prevailing Ptolemaic model, revealing discrepancies between theoretical predictions and empirical data. His mathematical methods, particularly his use of trigonometry, provided astronomers with powerful tools for analyzing celestial phenomena and developing new theories. The Kitāb az-Zīj translated into Latin and widely circulated throughout Europe, served as a catalyst for scientific inquiry, inspiring astronomers to question established dogmas and pursue new avenues of research. The modern relevance of al-Battani's work lies in the enduring value of his observational data and trigonometric techniques. While modern telescopes and instruments have far surpassed the capabilities of those available in al-Battani's time, his meticulous observations continue to be valuable for historical studies and for calibrating modern astronomical models. Long-term astronomical data sets, spanning centuries, are essential for understanding subtle changes in celestial objects and for testing the validity of astrophysical theories. Al-Battani's observations, carefully recorded and transmitted through the Kitāb az-Zīj, provide a valuable historical record of the night sky, allowing astronomers to study the long-term behavior of stars, planets, and other celestial phenomena. Moreover, al-Battani's trigonometric techniques continue to be employed in various fields, including astronomy, physics, engineering, and computer graphics. Trigonometry provides a powerful framework for analyzing periodic phenomena, modeling wave behavior, and solving geometric problems. The trigonometric functions that al-Battani helped to develop are fundamental tools in these fields, enabling scientists and engineers to understand and manipulate the world around them. The enduring relevance of al-Battani's mathematical contributions underscores the timelessness of mathematical principles and their applicability to a wide range of scientific and technological problems. Al-Battani's contributions must be viewed within the broader context of the Islamic Golden Age, a period of remarkable intellectual and cultural flourishing in the Islamic world. During this era, scholars from diverse backgrounds gathered in centers of learning such as Baghdad, Cairo, and Cordoba, engaging in the translation, preservation, and advancement of knowledge. Islamic scholars made significant contributions to mathematics, astronomy, medicine, and other fields, building upon the foundations laid by the ancient Greeks, Persians, and Indians. The Islamic Golden Age served as a bridge between ancient wisdom and modern science, transmitting knowledge across cultures and generations. Al-Battani's work exemplifies the spirit of intellectual curiosity and scientific inquiry that characterized the Islamic Golden Age. His meticulous observations, mathematical innovations, and commitment to empirical verification reflect the values that drove the scientific revolution in the Islamic world. The Kitāb az-Zīj, a product of this intellectual ferment, stands as a testament to the achievements of Islamic scholars and their enduring contribution to the advancement of human knowledge. Al-Battani stands as a pivotal figure in the history of astronomy, a bridge connecting ancient Greek astronomy with the scientific revolution of Europe. His work embodies a unique blend of observational skill, mathematical ingenuity, and intellectual curiosity. He demonstrated the importance of precise observation, the power of mathematical reasoning, and the value of empirical verification. His Kitāb az-Zīj served as a beacon of knowledge, guiding astronomers for centuries and inspiring them to explore the mysteries of the cosmos. Al-Battani's legacy extends far beyond his own time, continuing to shape our understanding of the universe and our place within it. His contributions serve as a reminder of the interconnectedness of scientific progress and the enduring power of human intellect to unravel the secrets of nature.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.